Hello everyone. Now we will solve our second problem. Discuss the role of sufficient statistics in finding this UMVUE. Already mentioned that for UMVUE, CRLB not enough. We need this sufficient statistics. How does Lehmann-Scheffé method helps to obtain UMVUE? Okay, based on Lehmann-Scheffé theorem, we found this one, and inside this Lehmann-Scheffé theorem, we had sufficient statistics. So let's understand this one. So here are been some of the roles that I have written. Data reduction, when there is a sufficient statistics, it will definitely capture all the information that parameter needs, allowing estimators to be based on only one TX, the sufficient statistics, instead of the full sample. So this is the advantage. And this is the primary role for sufficient statistics in finding UMVUE. Next one is Rao-Blackwell theorem. So as you know that the Rao-Blackwell theorem uses sufficient statistics to find out the UMVUE, or MVUE. Okay, so next one is the Lehmann-Scheffé theorem. Similarly, corresponding to Rao-Blackwell theorem, Lehmann-Scheffé theorem also uses the sufficient statistics to find out the UMVUE. So now in conclusion, what we can say? In conclusion, we can say that sufficiency helps in simplifying the search for UMVUE. So for UMVUE, the easiest way and the simplest way to find out this sufficiency by focusing only on the TX. When combined with completeness, it guarantees that the resulting estimator is the unique UMVUE. So next, if you find out the completeness, then it will be done for you, and you will definitely find the unique UMVUE. So next one, the next question that has been asked here was discuss how Lehmann-Scheffé method helps to obtain the UMVUE. So now we will see how Lehmann-Scheffé theorem, Lehmann-Scheffé method helps us. See, in this Lehmann-Scheffé method, there is a three-factor how we find that. But before that, the Lehmann-Scheffé theorem helps us to find out the UMVUE. Simple way. Okay, providing a system adequately funded. The theorem states that TX is a complete. First one is complete. Second one is sufficient and unbiased estimator for the parameter theta. If the theta estimate is any unbiased estimator of theta, then the UMVUE of theta is given by conditional expectation of theta given TX. So it's some kind of a conditional expectation. There is this conditional expectation. Thus the Lehmann-Scheffé method helps us to obtain UMVUE by identifying complete sufficient statistic TX for the parameter theta. Finding an unbiased estimator for the parameter of the interest. Calculating conditional expectation, which provides the UMVUE. So next one. So we done our second problem as well. The next problem is obtain MVUE, MVBE estimator of parameter mu and the sigma square from the density mu and sigma square based on the random sample. So this is the sample. Show that the variance of MVBE estimator coincide with the corresponding CRLB. Okay, for solving this problem, so do we have two parameters? Parameter of interest, the normal distribution has mean and the variance. Based on the random sample, show the variance. These are the two parts mainly. First of all, we have to find the MLE. By this way, we will find an estimator, and we have to prove that these estimators are MVBE. How we can prove that? Yes, we will use the Kramer-Rao lower bound, and this way we will prove that these two estimators for the normal density, it is MVBE, and also show that the variance MVB estimator coincide with the corresponding CRLB. So the condition that theoretical condition that CRLB provides, it's match with the MVBE, helping us to match with finding the MVBE. So we will see that, and that will be more a clear way to understanding that will be. First of all, we had a normal distribution. Okay, we had a normal distribution with the parameter mu and sigma square. So there is the identification. X is the data points, mu is the mean, sigma square is the variance, and these are all other population configuration. Okay, so our first task will be finding the likelihood function. So how we can find out the likelihood function? We have to just take the product of the PDF. So we go for that, finding the product of the PDF. Second one, what we can do, we write the PDF, exact PDF, and the next one we separate the terms. See, these are the product, it will apply for this part and it will apply on this part as well. So we separately written these two parts with the product. Okay, now there is an important factor. This product I1 up to n. Okay, this product, this I subscript, do you find any subscript in this 1 divided by root 2 pi sigma square? All other constants corresponding this product. So this product will be written as this one as a constant. And how this happens, see, written in the short notes, I1 up to 3, and this 4 is a constant respect to this I1 up to 3 because there is no subscript that contains the I. So when these are the constant, then will be this constant term will be multiplying 3 times because we go for 3 terms, and it could be written in 4 to the power 3. So if it is 4 to the power 3, then this n will be over the constant term, just like this one, because this one is the n here, right? This one is the n. So this n will be the power as a constant over this. And next one is the, see, I1 up to n. This I subscript contains in this x. Okay, and then so we will have application of this product on this only part, over the part, but not the denominator. Only the numerator will get the product. And how this product will be done here, see, for before that you will have to understand this one. Suppose e to the power 3, e to the power 4, and then e to the power 3 plus 4, based on the simple mathematical terms, and we will have e to the power 7. So there is happening the summation, right? Summation I1 up to 3 and 4, I1 up to 2, and the 2 are 3 and 4. So we addition 3 and 4, the addition has been applied. So the same way, the very same way, here the addition will be applied over the numerator, not the denominator, so that the denominator is outside, and I1 up to n. So this way the numerator got the summation, okay, by the condition like this one. Then what I have to do, simple way, we have to take the log likelihood. So we'll take in the log likelihood. After that, after we taking the log likelihood, yeah, we will get this one in terms of this. So these are the last steps. Then we will go for finding the maximum likelihood estimator. So these are the important factors. We will have our Emily for mu, and these are the Emily. Okay, now what we have to do, for this mu, we have to find this mu's variance of this mu. So finding the variance of this mu, because our main focus will be the finding the variance of these two parameters, mu and the sigma square. First of all, we go for mu, finding the variance. What we found, sigma square divided by n. Sigma square divided by n is our variance of this Emily maximum likelihood estimator. So now what we will do, now we will perform the Cramer-Rao lower bound. For that, as you know that already discussed, we need the Fisher information. Okay, we need the Fisher information. You can memorize that IU is n by sigma square, or you if you wanted to find out yourself, you will have to go for the same approach. Yeah, directly This part you already know in previous sections. Then you first you have to do the first derivative. We take the first derivative, then we have to do the second derivative, and the second derivative got minus n by sigma square. And by the Kramer-Rao condition, where the Fisher information is minus expectation of the second derivative of the log likelihood, we will found. So there will be two variances come from CRLB. We found a variance from direct approach from the estimator, a maximum likelihood estimator. When we take the variance, we got an variance as well. So two variances. When you just compare this variance to this variance, these two variances, previously variance of mu hat, we've already found that it is sigma squared divided by n. We write it in here like this one. So both of them satisfied the equal operation. So equal sigma squared divided by n. So we can say that yes, it achieves CRLB, proving that mu is the MVBE. So among two unbiased estimators, mu is the minimum. So this is our final answer. So next one, we done for the mu, the mean, and then we will go for the variance part. So generally we derived this one previously, so from that one we take the first derivative like this one, and equal to we take it as a 0, and we will find the estimate of the variance. So we found these estimates, and from this estimate we calculate its variance directly. And how we can directly, this is the, you can memorize this part, or you, if you wanted to find out how you done this, you will go for this how approach. And you see, when I just take this variance, what I found variance of sigma square like this one, and therefore you just deriving this way, simplifying this way, you will got 2 sigma square, sigma to the power 4 n minus 1, you will got it. And after that you will compare two variances of the population variance. So for Fisher information, we will got this one, and if you wanted to know how, you will go for this approach. Similarly, Fisher information, and using this Fisher information we found it this way, and after solving this we found the Fisher information like this one, and using CRLB we found this one. And there is now two things, one come from the CRLB and another one come from direct approach when taking the unbiased estimators variance. So see, this part previously we done on the variance of sigma square, and it is 2 sigma to the power 4 n minus 1, and it is greater than the come from the that come from the CRLB. So it's a valid. So when it is a valid, so yeah, it achieves CRLB, proving that sigma square MVBE. So we done for our two parts of the question.